Hello, everyone. Thanks for being here today with me. My name is Guillaume Laforge. I'm an engineer at Google, and I focus on generative AI. I've heard it's something quite trendy these days, right? And we'll be talking about a particular aspect of generative AI called retrieval augmented generation. And it's actually fairly trivial or easy to do a RAG implementation, but to do it right and getting good results out of your system is actually more complicated than you would expect. So a few links if you want to follow me or also have access to the slides, etc. And in this presentation, I'll be using my favorite framework, LangChain4j. So maybe some of you have heard about LangChain for Python developers, but there's a project called LangChain4j for Java developers. I'm also a committer on the project. It's an open source project. And I contribute in particular to the integrations with Gemini, the LLM provided by Google, Vertex AI tools. That's the offering of Google Cloud with all the AI stuff in it. LangChain4j contains various basic bricks. So access to language models, access to prompt templates if you want to have a reusable text with placeholders, etc. You have document loaders and splitters to be able to give access to your documents to the LLM, embedding stores, that's vector databases, etc. for doing vector comparisons. And we'll be using that in that presentation for the various code examples I'll be showing you. Let's start with the introduction, a rapid introduction to a naive RAG. So there are limitations to large language models. They have a cutoff date. So if you ask questions like in France, we recently changed, we have a new prime minister, but most LLMs, if you ask them, Gemini, ChatGPT, whatever, they have a cutoff date. So for example, I think for Gemini, the last drop of information was, I think, in August, so it's still like 6 months old. And if you want to ask questions about the latest news, the LLM has to have access to news search and that kind of stuff. So if you use gemini.google.com, it has access to news, so you'll get information that is fresh. The other aspect is, of course, LLMs don't know anything about your data, but I would say it's normal, right? Like your personal data, your customers' data, and documents, etc. But sometimes you do want to give access to that information to the LLM so that you can ask questions about your own data. That's why we're going to study RAG here. LLMs always try to answer something, even if they don't know, although you can ask them, please say you don't know if you don't know. But often they try to reply something. And when they don't know, they actually hallucinate and say stuff that is not correct or wrong. And there's also a limit to what quantity of information you can feed to an LLM. There are models like Gemini that we'll be using in this presentation, which have up to 2 million tokens context windows. That's huge. You can put all of Harry Potter books, all of Lord of the Rings books in the context and ask questions about the characters, for example. That's kind of impressive, in my opinion. Yet, the quantity of data that you have, and maybe you don't want to feed everything, you just want to put the relevant information in the prompts of your LLMs. So that's part of the limitations of LLMs. So retrieval augmented generation, the 3 letters, retrieval is all about how to search for information. You have a user asking a question and you want to search information related to that question. The augmentation is how you're going to pass the information that is retrieved into the prompt of the LLM. And the generation, well, that's the LLM that generates its answer. And usually there's a kind of common template that we use. You say, OK, you must answer the following question. Then you give the user's question. Base your answer on the following, extract, documents, etc. And the LLM will, so you replace the placeholders with the right data, of course. And then the LLM will figure out how to respond depending on what's given in the prompt. Some benefits: improved accuracy because the responses are really grounded into the information you give in the prompt. That's important. Reduced hallucinations, of course, because you give it the right information, so normally it should answer with the information that is there, not something that doesn't exist when it doesn't know about this particular topic. You are able to give fresh information and data, etc. Because of the cutoff dates of the LLMs. Here you are responsible for putting the latest information and to refresh that information when it needs to be refreshed. And I think that's one of the key aspects for me, explainability. Maybe we don't mention that enough, but it's actually show me your sources, because you can say, okay, here's the response, and it's based on those sources that were found in the vector database, in the search engine, etc. So it's important for your users, your end users, because they will see, oh yeah, it's coming from that document, so they can do somehow their own fact-checking or look further inside the documentation when you provide the links to the sources. So that's important. So let's have a look at more of the architecture. There are two phases, the ingestion and the retrieval, and then generation, of course. So initially, you have a set of docs, whether it's text, it can be PDFs, it can be images, it can be anything, or even data from a database. You chunk that information into small pieces, and you're going to calculate vector embedding. So that's a big floating point vector, which represents the semantics of the text, the chunk of text. Okay, so it's easier for LLMs to work with big vectors of floating numbers. And then you're going to store both the chunk of text and its associated vector in the database. Then comes the retrieval part, where you have your user and the chatbot app or any, so it doesn't have to be a chatbot, it can be something else, but let's say it's a chatbot app, so the user asks a question, it goes through your app, and we're going to calculate vector embeddings, just like we did for the chunks of text. And we're going to look for similar vectors in the vector databases. And usually, and I say usually, we'll see why it's not always the case, usually the vector of a question is more similar to the vectors of the text that can contain the answer. So semantically speaking, a question and an answer are linked, and it shows in the values in the vectors, so the vectors point in the more or less right direction. And we are going to do, so the prompt, like I mentioned earlier, here's the user's question, please answer with the extracts in the extracted information, and then the LLM generates the answer. So far, so good. However, there are many places in that diagram where things can go wrong, can be suboptimal, let's say. So for example, how did you load and parse the document? Maybe there's a format that would be better than another, for example. I said we chunk because we split into smaller pieces of text to find units, I would say, of semantic meaning. But sometimes maybe your chunks may be too big or too small. Too big chunks, maybe the meaning would be super diluted in a big paragraph. And if it's too small, maybe the information is cut and you're missing some important bits. Is the context, the chunk context relevant? So what you actually put in the prompt of the LLM, is it relevant or not? Because maybe it's been retrieved, but it doesn't contain the answer to your question. Did we embed and store all the information? Maybe we missed something. Is the question, I mentioned that, usually a question is close to its answer, but we'll see techniques to improve that. Did the LLM really include the answer? So we nudged it to say, okay, reply with that information, but maybe it can potentially say something different or use its internal knowledge instead of the information that we gave. So that's why we're going to study various techniques. So we'll look first at the ingestion part. So this is this part here. And the first thing we're going to have a look at is the chunking phase. Can we improve chunking here? So I'll cover some of the chunking techniques that I've worked on. And let's start with this one and some context. So I take a page from Wikipedia about Berlin. I extract the raw text. So that's also part, if you have to extract like the right information. You don't necessarily need all the Chrome around it. So you just want the raw text. So data, document loading and parsing is important there to use the right format. If you look at this, maybe I want to ask what's the population of Berlin, and how can we do that? So we see that the answer is here, but we'll see some tricks. So one way, a classical way, is to split the text into chunks of text. For example, 100 characters. Why not? So usually we usually use between 100 and 500 or 1,000. But usually, let's say 200 is good. But here I chose 100 for a very specific reason. If you look at that little point there, and here, if you cut by 100, the information, like the numbers I'm interested in to know the population of the city, is split across two chunks. So neither the reddish chunk contains the answer to the question, nor this orangish kind of color contains the answer. And same thing here, another number is split in two. So one way to avoid that is to do overlaps. So the first chunk goes blah, 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 up to here. It's cut. Well, it's OK, because the next chunk, the orange chunk, will start a little bit earlier. So you see that the new orange will start here. So you really have the actual number of inhabitants. Another approach to avoid those cuts issues is to chunk by sentence. It works great, and usually human beings, when we write sentences, we know there's a unit of semantics, a unit of meaning in a sentence. So it could be a good way to split things, but it's really good for text data. Maybe if you've got like tables or things like that, how does it work? What is really a sentence there? Is it a cell, etc.? So, but there's something that is a little bit problematic here. It's the fact that, OK, I know the number of inhabitants in Berlin, but if you look just at this orange sentence, it doesn't mention it's about Berlin. So this its pronoun points at Berlin, but it doesn't contain, the chunk doesn't contain the information about the name of the city. So maybe when we search population of Berlin, maybe it's not going to return the right chunk, or maybe if it returns that chunk, the LLM won't be sure it's about Berlin. If it's returning that chunk here in the vector search, maybe it won't know the number, but it will know it's about Berlin. OK. So it's not ideal. So one way is to use, so I don't really have a good name for that, but a parent-child kind of relationship where you do different levels of chunking. So you have a chunking first by paragraph, and then a chunking by sentence. And here, what's the actual approach, which is interesting here, is to calculate the vector embeddings for getting the numerical meaning of a sentence. But to the LLM, when you prepare the prompt, you're going to return the whole context of the paragraph. That way, this one matches the question quite well, but you also have the extra information from the surrounding sentences, surrounding paragraph, so that you know that Berlin and it's, that's the same thing, so it's Berlin has that many inhabitants. And so we embed the sentence and return the whole context. One problem maybe with this approach is that, like for big books, like novels, etc., let's say paragraphs can be super long, that they can be many pages long potentially. So a little tweak I did to that approach, which is also inspired by a paper. So I usually try to give some links to relevant sources of information about this, is I'm doing a sliding window of sentences. I'm not looking at the paragraph, I'm looking at a sliding window. So I'm going to calculate the vector embedding again for just that sentence, but give the whole context to the LLM. So let's have a look at some code here. So this is what I'm doing. I'm loading my document. Let's me moving here. So I'm loading my document. I'm going to split the document into 200 characters with an overlap of 20 in case the sentence is bigger than 200. It's going to be further cut, but otherwise it's just the whole sentence. And then I'm calculating the splits. And I have a little function to do a sliding window where I specify the number of sentences before and after. And then I'm going to calculate the vector embedding. I'm getting the vector embedding first. I'm going to use a little in-memory vector database for this example. And here, that's where I'm going to calculate the vector embeddings for each sentence and add the actual surrounding sentences in the context. And here, let's have a look at the search. So I'm going to say, OK, I want to search my vector database with maximum of 4 results, score of 0.7, and I'm going to embed the question as well to compare the vector of the question with the vectors in the database. And then I can show so the similarity, where is it? Then I get the chat model, and I have my little template here. You must answer the question with this extract. And I show the answer. So let's run this. Up. It is here. So I've already run it to go faster. So I've split everything into sentences, and we'll go straight to the end. There are lots of sentences there. So where is it? Whoop. Yeah. So what's the number of inhabitants in Berlin? And I have a score of 0.91. And I actually calculated the embedding for that, but I gave that in the context of the LLM. And so I have the answer there, and I have the name of the city. So the LLM will figure out that, yeah, that's the population of Berlin. Then I have some other documents that are returned with quite good scores as well. And it mentions other aspects like the population of the region, etc. And then what the LLM responds is the following. So there are different figures that are returned. So within the city limits, yeah, that's 3.85, but there are also some other numbers. So maybe you could ask to be more concise in your answer, etc. You can tweak the prompt as well. All right, that's it for this first example. Another one that I quite like, as I said, so questions and the vectors are close to, questions and answers are close to each other in the vector space. However, not always that close. And there are vector embeddings. For example, the one I'm using here, it's a vector embedding from Google Cloud, or for the Vertex AI offering, which is actually good and specialized for some tasks. For example, it's good at fact-checking, it's good at calculating similarities between documents, etc. And there's also a specific task that you can configure to say, OK, your job is to respond to, well, Q&A, basically. So questions and answers, and it's going to calculate embeddings a bit differently so that questions and answers are really closer than, let's say, by default. So this approach is a little bit different from the other. The idea is that you're going to embed a hypothetical question. So I'm going to chunk here by paragraph, and I'm going to ask an LLM to come up with questions whose response would be the actual piece of text. So in this text, I ask for potential questions. So what's the capital of Germany, population? And that's the LLM that generates the questions that match this text. Okay? And when you do this, what you're going to compare in vector space, that's going to be a question and the user's question. So if you compare questions and questions together, they will match and have a higher level of similarity. The vectors will be closer. So if you look at this in the code here, yeah, hypothetical questions. So again, I split by paragraph, and then I ask the LM to suggest 10 clear questions whose answer could be given by the user-provided text. And also, I give some precision, like don't use pronouns. Be sure to like replace it's with Berlin, etc., so that there's no confusion and we're sure about the topics. And so I parse the output. I'm calculating again the vector embeddings, and I store them in the vector database. And here, that's where I'm asking the question. So again, I'm doing my search, similar to earlier. And we'll have a look at, so what was, yeah, I'm using, so let me show you actually the output. That will be easier to see to understand this. So that's here. How many inhabitants are there in Berlin? And it found in the vector database this question. And this actually matches quite well with this question that I embedded in the vector database. And you see that the score is better. Instead of 0.91 I think we had earlier, we have 94, which is better. And you have several chunks that are returned. And then, so I think it's here. So reply to the following question with this extract, and then it's going to return a more concise response, actually, with just, at least this time, with just the information from the first paragraph. And interestingly, I think, yeah, all the other questions return the same segment, because that's really the one that matches the question best, and that actually contains the answer. So it's a nice technique that I like very much. Another approach is contextual retrieval. That's Anthropic wrote this blog post. You have the link at the top. 6 months ago or something like this, which suggests another approach. So it's a bit similar to finding questions related to that paragraph, but it's a different twist. So instead of asking questions about that paragraph, it actually tries to situate that particular extract, like the chunk, let's say a sentence or the paragraph in the whole document. And you're going to give the whole document each time. You're going to give a chunk, sentence or paragraph, and then please give a short, succinct context to situate that chunk in the overall document. And it's working well. However, you have to remember that you're going to ask an LLM to do this generation each time with the whole document. So that's going to consume lots of tokens. So that's a costly approach. It's certainly great for Anthropic because you pay by the token. However, even if it's efficient, maybe it's yeah, a little bit costly to go through that. And here, so I took a different example, but I used the prompt. So I'm using an example with dimensionality reduction techniques. And I used the prompt that Anthropic provided. And I do the same thing as earlier. So I won't show you all the details. And I'm storing this actual context. And for example, let's have a look at, let's say, this one. That's the original text, but contextualize. This is introductory paragraph about this and that. And the one I'm going to be interested in, that's, I think, probably this one. This one contains a list of techniques for doing dimensionality reduction. And it says clearly the section list common dimensionality reduction. So if I ask the question, what are common dimensionality reduction techniques? It's going to match against that vector. And it will return this information, which is very interesting because my question, what are the techniques for dimensionality reduction? It's not really mentioned in that paragraph, right? There's the word technique. Yeah, dimensionality reduction is mentioned there. But it's not a paragraph that says, here are dimensionality reduction techniques, okay? So the context is interesting because it matches better with the user's question. And if I go like at the bottom, so what are the main dimensionality reduction techniques? And this paragraph seems to have high similarity, although the ranking, if you do the ranking, it's quite low, interestingly. But at the end, I don't know if I generate the answer. Yeah, I generate the answer here. and the response. Yeah, here are the different types of techniques. And I think it also adds a bit of its own knowledge because it seems longer than the paragraph that I had in my original data. Yeah, so embed the chunk in context. Another one that was popularized by Greg Camerat, it's semantic chunking. The idea is to look at, let's go with the sentences, to look at every sentence and compare each sentence pairwise, and to try to find, oh, at that point, this sentence and this sentence is way more dissimilar than those two others. And you're going to find this distance between chunks, and you're going to hunt for the ones with the biggest difference. And you might think that the chunks before can be grouped because they are more similar, and the chunks after that breakpoint are also similar, so you might group them together. So you split by groups of chunks at particular points, particular breakpoints, where there's, in terms of semantics, the difference is bigger. So I tried this, I implemented it. I'm not super happy with it. I don't think it gives the best results. However, I tried different things like doing, again, sliding windows to average a few sentences together, because sometimes you may have like one sentence that, like a digression or something that points at another interesting article, but that's totally unrelated to what we're saying. And sometimes you may have a breakpoint at that point, although the whole two paragraphs before after are about the same thing. Maybe there's a sentence that's going to be a breakpoint. So maybe using average seems to be better, but I'm not super convinced with this technique, but it's probably better to just chunk. If you have a very structured document, it's probably better to go with the structure of your documents, like part 1, chapter 1, first section, etc., because you already have the semantic meaning and grouping of semantic information by paragraph or sections. So it would work better, in my opinion, than semantic chunking. At least that's my experience. Yeah, I mentioned a better embedding model. That's embedding models that work, for example, across many languages, for example. If I have documents in different languages, I have to be sure that I use an embedding model that understands the various languages, or that is able to support different tasks. I mentioned the tasks earlier, like doing Q&A, doing similarity calculations for documents. Another thing, very quickly, a more powerful database. For example, if you search through just a subset of the vectors, you're going to have potentially better results, because maybe I have all the chunks for Berlin, but I have all the chunks for Paris, for Stockholm, etc. But if I know the questions are about Berlin, then I can just return the vectors about Berlin. So you have to nowadays, most databases allow you to do some filtering, but filtering, so like a where clause, basically, with SQL, it's going to find the vectors just in a subset, which subset that is more relevant to the question. So let's have a look at the retrieval techniques. So query compression. Query compression is the fact that you have the dialogue in the chatbot, so the user may be asking, hey, what is the capital of Germany? Okay, it's Berlin. And then the next question, where is it situated? Okay, it's part of Europe, it's placed here in Germany, etc. How many inhabitants are there? But if you look at those questions, usually what you do when you do RAG is you search for the last question that is asked. And the last question that is asked is how many inhabitants are there? But you've got no details about where, actually. Is it Berlin? Is it the country or something? So you can ask an LLM to compress the ongoing discussion so that the last question contains the context of that discussion. So the LLM, Gemini or something else, will create a new question that is more precise and contains the information. So how many inhabitants live in Berlin? Instead of the original, how many inhabitants are there? Query compression. Shall I show you this one? So yeah, I have the 3 questions in a row. Yeah, but I'm not showing the synthesized questions, so it's not very useful. I should show that in the example. But you'll be able to, at the end, I have a link to all the code samples if you want to have a look. Query transformation. So if you remember the hypothetical questions approach in the ingestion phase, this is a bit equivalent, but at the retrieval phase. So instead of searching what is the population of Berlin, we're going to search for an hypothetical answer. So we're going to ask an LLM, even a small LLM. It doesn't have to be a big LLM that knows everything. Maybe the LLM will say, OK, there are 3 million inhabitants in Berlin, but you're going to search for that hypothetical answer in the database. And you're going to compare answers and answers. And you're going to find a good match here, because this sentence talks about million something, about inhabitants, and this 3 or couple sentences mention Berlin, population, inhabitants, million, etc. So it's going to retrieve better results. All right, I could show you, I think I have it, yeah, it's here, hypothetical documents embedding. I'm using the dimensionality reduction again, and I'm going to show the results with a normal search and the results with a hypothetical question being used. So if I come back, I've already run this. So what are the common dimensionality reduction? The hypothetical answer is the one generated by the LLM. So if I do the search directly without using the technique, okay, the first chunk, 0990, first chunk, good similarity, but doesn't contain the answer. This one, good similarity, but again, it doesn't contain the answer. Third, fourth. So the fourth, with a lower similarity, actually contains the list of dimensionality reduction techniques. Interesting. Now, if I do with a hypothetical answer, the very first vector that is returned, the first chunk that is returned, has a much higher score, 95 instead of 90, and it is the one which actually contains the information I'm looking for. So you can see that if you go with a hypothetical answer, it's going to match better with what you have stored in your database, with a higher similarity, and it even comes first, whereas with the normal search, without doing this technique, the chunk containing the answer was in 4th position instead of first. Hypothetical, oh yeah, query routing. So there are different ways to do query routing, actually. I'm asking questions about Berlin. But let's say, so all the data I have in my vector database is about Berlin, but if I ask a question about Paris, about Stockholm, it doesn't contain the information. So the LLM won't be able to reply, and the vector database won't be able to retrieve the good results from the vector database. So instead, you can do query routing, which is, okay, I will search the database if it's about Berlin, or I will use, for example, web search or another database if it's about something else. Retrieval, where is it? Query routing. Query routing is here, and here I'm using higher level components. I was using more low level to show you how to do that, but here we're using Longchain4j's AI services component, which is higher level, because you can plug things together. So for example, I defined a search engine. I'm using Tavily Search, a nice little search engine. I'm defining a content retriever, which points at this search engine. And I have a query router, which either points at Berlin or web search. So if and then I'm going to add or augment the LLM prompts, etc., with an augmenter that will so we pass it here when we create the assistant. I'm going to retrieve via this augmenter, and it's going to either route to the Berlin or to the web search. And if you do that, well, I'm just showing the answer, but basically I ask a question about Paris, and it's not very visible. I should add some more logging stuff because it's just replying with a search from Tavily search, which goes through the Google search index and so on, instead of going through the Berlin document because it doesn't contain information about Paris. Metadata filtering, so that's when you actually, so let's say I have a big database of all the capitals in the world, and then I want to just filter the ones I'm interested in. So for example, again, if I ask questions about Berlin, I just want to have vectors about Berlin. If I ask questions about Stockholm, just the vectors about Stockholm, because it's going to, when you ask for, let's say, 5 search results with the vector database, you don't want to have other similar vectors, but that are from other cities, basically. So you can say, okay, I know this question is about Berlin, so I'm just going to search the vectors about Berlin, but not vectors about Paris or Stockholm. Yeah, I won't show this one. Reranking, that's in some of the example you saw. Sometimes I was using there was an indicator, so there was the similarity, but there was also a number which was the reranking. Reranking, it's some specific kind of models whose job is to say, okay, does this chunk of text answers that question? And you don't need big models to be able to do that. And when you use that, it gives a confidence score, like the similarity. And then you can reorder all your segments that were ranked by similarity, but you reorder them thanks to a reranking service, a reranking model. And usually it will push up the results which really contain the answer, so that you pick from the top rather than returning all the results. I think I have an example, yeah, here, and it's you just add like yeah, it's called a scoring model. So I have my scoring model here, and I'm going to pass the scoring model somewhere. So where is it? Scoring model is used here with the content aggregator. So it's another notion of Longchain4j. And then for the retrieval, you pass the content retriever, that's access to the database, and the content aggregator, which is going to reorder the search results. Did I run this one? No. Okay. So we'll go with Agentic then later on. So quite a few interesting techniques to improve the results. There are other aspects to keep in mind, but it's not so much about having a better results, but like you could use response caching to cache common responses to the common question that come very often. Maybe everybody asks about the population of Berlin. I don't know, so you could cache that. But yeah, it's a bit beyond this aspect. So I'd like to talk about function calling and agentic RAG. Agents, you're going to hear about agents a lot this year, I think. And function calling works like this. So it's a way to extend the knowledge of an LLM by giving access to some functions. So for example, let's say I want to ask what's the weather in Paris. It's going to ask the LLM the question, what's the weather like in Paris, but it's going to give access to a function. So the LLM will know, okay, I don't know the answer to that question, but if I could call the getWeather function, maybe I would be able to reply. So you get that response back. Okay, please call getWeather for me. And your application automatically, when you use Longchain4j, it's done automatically. You're going to call that getWeather application. So the gray stuff is stuff that is not seen by the end user. So it's ongoing discussion between your app in Longchain4j and Gemini, or the model that you use. You get the weather, you call an external API service, and it says, okay, the forecast is sunny. And then the app is going to send back, hey, I got this response for this request. And now the model knows, oh yeah, I know, it's sunny in Paris, so it can reply, it's sunny in Paris. So why do I speak about function calling? Because that's a key technique for creating agents. So what are agents? So it's an app that uses LLM, obviously, but with a few extra things. So planning, maybe it's a multi-step approach to reply to some queries, to do some reports, to do some computation, etc. It has tool use access, so it can do multiple function calls to request information. You can add some reflection aspect, for example, a self-critique loop. If you want to improve, for example, you could say, okay, generate some code, but maybe you'd have a tool that is able to compile the code and report compilation errors, and then the LLM, oh yeah, I know there's a compilation error, let me fix the code, and with a few loops, maybe it's going to give you a better code, for example. And multi-agent collaboration, it's usually because it's rare that you would have just one AI agent, but you have smaller agents talking to each other. So let's have a concrete example of this with an Agentic RAG approach. So this time, instead of having simple questions, maybe we'll go, for example, the user may ask, hey, tell me about the origins, the population, the geographic situation of Berlin. Hey, that's actually 3 questions, right? So an approach, an agentic approach, is to call an LLM and ask it, here you specify the planning, but you could also let the LLM figure out what are the steps it needs to do. But here I gave an explicit plan. So the plan is first identify the topics. So there are 3 topics, origins, population, and geographic situation. Then I'm using the hypothetical question database, so that's why I'm asking it to create questions associated with each topic. And then I'm going to do the RAG search for each individual topic. So I'm going to do a RAG search for the origin, I'm going to do a RAG search for population, I'm going to do one last one for geographic situation. So 3 RAG searches. And I'm going to collect everything together and give a final report. So this agent has access to one tool, let's say a history geography kind of tool, which does the RAG search, which so it gets the answers, and it's going to call another agent whose job is just to study the topic, the answers, and create a report on just one topic: population, origin, geographic situation. So it's returning one report. And this tool is going to return all the, well, for each call, basically, it's going to return each topic report, and then the main agent is going to return the final report, which is the synthesis of all these questions and answers. So let's have a look at this one here. So as you can see, so where does it start? Let's have a look here. Here I've got a system instruction where I specify the planning. So that's what you had on the slides, basically. And for that assistant, I'm going to pass my history geography tool. So let's have a look at this tool. And this tool is actually a bit similar. That's a bit like the Inception movie, because you have yet another interface where you're going to say, OK, search for information about geography, blah, blah, blah. And then we're going to return the final answer if you look at the output. So it's going to invoke the ones for a what's the population of Berlin. It's going to do that for where is Berlin situated. And maybe for some topics, it's going to make different calls. And then, so you have the topic reports each time here. And at the end, it's going to generate a bigger answer, population, geography, etc. So for more advanced kind of questions, it's interesting to use such approaches. Very quickly, I'll mention that en passant. Evaluation is critical, because if you use those techniques, you have to somehow evaluate the techniques and see if they make a difference in the results that you get. So you should have some set of questions that you should ask and check that, OK, I use this technique, it seems that the responses are better, because you have to evaluate to be sure that it's worth using that technique. You can sometimes also use LLMs as judge, so that they can so that they can judge if answers are correct or not, or also to prepare synthetic data to feed and do the evaluation. Yeah, response is correct. Keep in mind security concerns. I'll brush up on that. Things like hiding personal information in the logs that you have, etc. That's all the things to keep in mind. And one more also to keep in mind is that data is staying alive. Ooh, ooh, ooh. No, I won't sing, don't know, or I won't dance either. The thing is that you have to remember that maybe at some point a document will be outdated, so you will have to remove the vector embeddings for that old version of the document to update and create new vector embeddings for the new version of the document. So keep remembering that data is alive and has to be updated. So time to conclude and maybe have a few questions. There are questions that are easy and questions that are much harder. So simple yes, no kind of questions, they are easy, or finding like the altitude of a mountain, it's easy. But then there are questions, especially what I call the multi-hop kind of questions are much harder because they require several hops, several questions before you can actually give the final answer. So who was the quarterback of the team that won Super Bowl 50, blah, blah, blah. You have to, okay, Super Bowl 50, team who won, then who was the quarterback of that team? So you have to ask several questions before getting the answer to that very specific question. So that's where things like Agentic RAG approaches work better, or using, I didn't talk about this, but if you go to the Neo4j booth, they'll be able to talk to you about graph RAG, which is yet another approach, especially for linked data. It's a super technique. And often I get the question, yeah, well, you showed several techniques, but which one should I pick? Well, it depends, right? So you have, for every use case, maybe, I mean, depending on the use case, one technique will work better or not, and there's not one response. So you have to try a few and see which works best for you. So thanks a lot for your attention. All the code is available here. It's on the DataStax GitHub account because I did this presentation with a friend from DataStax, and we worked on the codes together. So yeah, thanks again for your attention, and I'm happy to answer questions. Any question? Yes, Red Hat.
Where is the breakpoint when it's worth putting stuff into the vector database when you're dumping it into context?
Yeah, so where's the breakpoint? When to use a vector database versus putting stuff in the context? It depends on the size of the document that you have, basically, because if you know that everything can fit in the context, maybe just go with an LLM that has a big context window that can work well. However, there are also some downside in the sense that it's going to cost a lot of tokens, obviously, if you put huge documents in the context. And also generating the answer is going to be slower because it's also proportional to the actual length of what you give the LLM. So if you want to have a chat, if each time you pass the whole document, you're going to get responses maybe 20 seconds later, and in terms of user experience, it's not necessarily great. But another approach which is interesting is to do a search for some documents and actually put in the context different documents, full documents rather than chunks, and then taking advantage of LLMs are really smart at what's in their context. So if you have a complex question, maybe it'll find the answer in the whole documents rather than some small extracts from here and there.
All right, I think it's time to wrap up this session. Thank you very much for joining. It's time for lunch. Don't forget to rate the sessions you attend. You can do that at gfocus.se.